my name is Ramakrishna, and this is question 6 of the end semester examination assignment of the course Mat104. So, what this question asks of us is that we've got this equation and we've got to solve the ODE, but first we've also got to interpret what this natural phenomenon would be for a mass spring system. So I'm going to go on a limb here and say that it represents impulse, since this is the delta function, right? And what the delta function represents in a way is that we've got this object, or let's say the trajectory is sticking to 0, and as soon as we reach a certain point in the graph, right, which is for example this constant k, and exactly at this point when it's tending to this point, it will rise to almost an infinitely large amount, and then it will drop back as suddenly as it rose to 0, right? And so if this is the graph, right, this is the graph, then, and this is the y-axis, these are the y-axis, and this is the x-axis. So you get what I'm trying to say, right? And this is almost exactly what impulse includes, which is that there's a large amount of force in a short or in a very small time, small period of time. This is in a way a result of the delta function. Obviously this is what the delta function stands for. Let's say the delta function is delta t minus k, right? What this represents, what this represents is that it is this function integrates to infinity when it is at t equals k, and it goes to 0 at t equals not k, right? That's what we're trying to say. Now what we have to do is that right, we've also got to interpret, or we've got, without solving, we've got to come to a conclusion of what the graph is going to look like. So here, right, we've got k is 3 pi for us, k is 3 pi for us. I'm going to assume that this is the graph of the function. This point is 1, here we've got -1, right? And the trajectory says that it's 0. As soon as we reach the point 3 pi, we've got, let's say, a sine graph, right, which periodically moves between negative and positive 1. This is what the graph should be according to me. And oh, I'm so sorry, I forgot to mention one thing. This here, the area under the graph will be equal to 0, which will be equal to 1. I'm sorry. So this is what I believe the graph is bound to look like, right? Since there will be no, what we call in physics, damping, this graph will never it will be unending, obviously. Without taking into consideration air resistance and all these other um, trivial but real life phenomenon. Now we've got to solve this ODE, right? What we're going to do is we're going to use Laplace transforms. So we're going to say that this is equal to this. Now we can just separate these two using the properties of Laplace transforms, and let's just say we take 16 out. Right, and we've got this quantity here. So I mean, what we've already solved in a previous question, this can be written as this can be written as, I'm sorry, I'm jumping to conclusions. L S times L dash S times L Laplace transform of y dash minus y dash of 0, right? And this right, and we already know that y of 0 is 0, y dash 0 is 0. That's what's been given to us uh, to use. So we can negate this, and from here we can jump to another conclusion, the one I was jumping to before, which says that this quantity is equal to right, and again we know that this is 0, just like this, because we've been given y at 0 is 0, y dash at 0 is 0. So we can go ahead and say that s square L of y plus 16 L of y is equal to L of 4 times delta t minus 3 pi, right? uh, Now we know, I mean, we from what we've studied, that the Laplace transform of a delta function yields this result. So to simplify our result, let's just say, just like we pulled 16 out of the hat, out of the Laplace transform here, we can pull 4 out of this Laplace transform, take the Laplace transform of this delta function, and boom, we have the Laplace transform of this delta function, which will result in e to the power negative 3 pi s. So what we'll do now is we'll say that L of y, right? I mean, simply put, we'll just take L of y common here. We got s square plus 16, and we'll take s square plus 16 to the other side. We're cutting through some steps here because that will just make our life easier. E to the power negative 3 pi s divided by s square plus 16. We can go ahead and take the inverse Laplace transform of 4 by s square plus 16 multiplied with e to the power negative 3 pi s. And I mean, from repeated practice you get you come to these conclusions that this individual Laplace transform, um, this individual calculation is actually the Laplace transform of sine 4t, right? I already talked about how this is probably a sine function. This is a graph of a sine function, which was a broad, I mean, it was a very basic assumption given as how I'm doing this question for the first time. And right, so we can say that we've got y right. This is what we're getting so far, and this result, right, when you get the L inverse, the Laplace inverse, it's written in the form, it's simplified in the form f of t minus k, right? K here is oh, well, k here is 3 pi, multiplied with the unit step function t minus k. Again, k is the constant. So what we get is y equals sine 4t minus 3 pi multiplied with the unit step function of this form. As simple as that. Thus, from this we can draw a graph that justifies our or validates our assumption from earlier, right? So this continues, and this is the graph we get. So obviously this is unending, this graph is unending. The period is pi by 2, so you get 3 pi plus pi by 2, of course. And this is the graph you get, and it's, as you see, it's almost exactly the same as this, although I did it in a hurry, so it does not seem to be the same. And that is the proof and answer for question 6, the final of the end semester assignment for MAT 104. I've been Ramakrishna. Thank you for watching. Good night.